Welcome back to Physical Geology. Today I want to look at topographic maps. We'll be looking at two ways of locations on topographic maps. One is this latitude and longitude method, and the other one is a U.S. public land survey. Latitude and longitude are coordinate systems, and the key thing is that a latitude is really a distance measured north and south from the equator. And the equator is chosen because the equator is a great circle. And a great circle is one that goes around the full 360-degree circumference of Earth, the largest circle of all these parallels of latitude. As you go north or south, the circles or the parallels to the equator get smaller and smaller and smaller. So they're not unique. So there's only one unique one, and that is the equator. That's why it's called a great circle. Since we are looking at a distance on one of the great circles as we're going around here, especially if we're going from the equator to the North Pole or to the South Pole, as you're going north or south, you're also traveling along a great circle, and that'll be along one of these meridians of longitude. And so if you're going north or south in terms of parallels along a meridian of longitude, you're going to travel some distance. And that distance is a nautical mile. And so we measure this in degrees. So 1 degree is nautical miles. Because we are thinking about an angle, if we can sort of think about how this would look, if we would draw some angle, let's say that angle there is 1 degree, then I can take that 1 degree and I can divide it into 60 minutes. And I can take 1 minute and I can divide that 1 minute into 60 seconds. So that's how we're going to break these out. It goes in degrees, minutes, and seconds. To complete 1 degree, you need 60 minutes. So if you have, for example, this 34 degrees, 23 minutes, 23 seconds, well, that's not quite 34 and a half. It's maybe 34 and a third, because you're not quite to 34 and 30 minutes, right? So 30 minutes would be half a degree. And the other thing is 1 degree on one of these great circles is 60 nautical miles. And so that's where we get the distance. And it equates to about 69 regular miles or 111 kilometers. Now, when we're looking at longitude, we can determine our longitude by looking at the North Star and our local horizon. So that's what this is showing here, is that wherever you are on Earth, if you look at the North Star, and note that all these line of sight to Polaris are parallel, because the North Star is so far away that anywhere on Earth, when you're looking at it, you're basically looking at a parallel line. And then you're going to compare that line of sight to Polaris to your local horizon. If you're at the North Pole, the North Star is going to be directly overhead, and you get a 90-degree angle, so you're going to be at 90 degrees north latitude. If you're at the equator, you would see Polaris on the horizon. It'd be on the horizon parallel to your line of sight to Polaris. So there's no angle between your line of sight and that of your local horizon. So you'd be at 0 degrees, and that's the equator. Somewhere in the middle, whatever angle you measure between the line of sight to Polaris and your local horizon, in this case it's 60 degrees, then you're at 60 degrees north latitude. So read a little bit about this, and there's a couple of questions that are going to ask you to determine your latitude based on your line of sight to Polaris. On the next page here, we're looking at drawing some angles. So you will need a protractor for this exercise. And for this first problem, they're going to ask you to measure the angle between A, B, and C. And here I've already measured it for 45. But the way you want to use this, remember the bullseye has to go right at the angle you want to measure. And then you want to have the 0 value right here, right parallel to the bottom of the triangle here that you're going to measure. And so here, when I look up here, I go 10, 20, 30, 45. So somewhere between 40 and 50. So that gives me the 45-degree angle. One of the problems later on is going to ask you to measure the angle between A, B, and C. So again, now you're going to flip this around, put the bullseye right at the angle you're going to measure. Make sure you have the 0 right there. And so this is going to be about maybe 20, 23, 24 degrees down here for this angle between A, B, and D down here. This problem here, for problem 5 here, that is going to have you look at figure 4. You don't need a protractor for this problem. For this one, you're just going to estimate, right? You're just going to look to see where the point is. For example, this point E is right at 20 degrees south. That's really easy. But point F, you know it's somewhere between 0 and 20 degrees north. It's a little bit less than 10 because 10 is this line right here. That's halfway. So maybe it's 9 or 8 degrees north. So just make an educated guess. So don't measure with a protractor here. Just make an educated guess and write those numbers down here for problem 5. And then this problem 6 deals with Polaris here. Now the next section, we're looking at these meridians of longitude. And like I mentioned earlier, every meridian of longitude goes from the South Pole to the North Pole and back down to the South Pole. So it makes one complete circumference of Earth. So each meridian of longitude is a great circle. So all meridians of longitude are great circles. When we're trying to locate, we're going to be either going to the west of the prime meridian or to the east of the prime meridian. So this prime meridian is the 0 degree longitude, and it coincides with Greenwich, England. And Greenwich, England is the home base for the British Navy. And so they make all their topographic maps based on 0 being their home base, the prime meridian, and then they're going to measure anything to the east, so this becomes the eastern hemisphere, or anything to the west. And so if let's imagine this is the 0 degree prime meridian, then you're going some numbers larger in this direction. Let's say over here we got about, let's say there's 20, 40, 60, let's say this is 80 degrees west over here, and here 20, 40, 60, 80 degrees east. So you're going larger numbers away from the prime meridian. When you get to the other side of the planet, the other side of the prime meridian is the international date line. So that would be the 180 degree longitude. Right? So the 0 degrees and the 180, it's basically the same meridian. It's just that it's the other side of the planet here. For this next part down here, you're going to be asked to sketch the prime meridian on figure 3 back over here on page 2. And so here, I would just call this the prime meridian. So that's going to be our 0 degree. And then they ask you to sketch in a couple of other meridians. So you can just kind of freehand some meridians that go through here. So there's one there, and we can sort of like wedges of an orange. If you think about how an orange is shaped, these would be like the wedges of an orange. And these are all those meridians of longitude. And then you can just label these. Maybe that's 30, 60, 90. So anyways, that's this question for 3. So you have to go back to page 2 on that one. This next part here, you're looking at, again, you're not measuring with a protractor here. All you're doing is estimating the longitude of these points. For example, this point B down here, we know it's at 45 degrees west. But point D, we have to estimate. It's something less than 15. It's probably more like 10 degrees west, right? So if I drew a line right to the middle here for the halfway point, so the halfway point would be like 7.5 degrees. So that's a little bit more. Maybe it's 10 degrees west. Now for this next part on quadrangles, I want you to read through this, but essentially quadrangles are this rectangular sections that represent an area of Earth. And because they're going to be in they're going to be in minutes, 15-minute series or 7.5-minute series, they have an area that they're covering. So if you think about a 15-minute series, well, a 15-minute series is about 15 nautical miles. 15 nautical miles. Because if you're going 15 times 4 is 60. So understand that these represent areas. They're 15 degrees on the side. For the 7.5-minute series, there's 7.5 minutes or 7.5 nautical miles on the side if we were on great circles. All topographic quadrangles will have north on the top, south on the bottom, east on the right, and west on the left. So that's something to remember. Let's look at some important features of topographic maps. And I downloaded a map here. And so here's a map, and they're produced mostly by the United States Geological Survey. And one of the first things I want you to look is you look in the upper right-hand corner, and this map is called the Haypress Valley Quadrangle. It's in California, and it is a 7.5-minute series. And for example, note that the eastern longitude is 120 degrees 30 minutes. But then when I go to the west longitude, it's 120 37 and a half, right? So I've gone from 30 minutes to 37 and a half. So that distance from here, from this west end of the map to the east end of the map is 7.5 minutes. That's why it's called a 7.5-minute series. So when I look at the latitude, in fact, let's look at the bottom here. And so the bottom of the map, the latitude is 39 degrees 30 minutes. So the top should be 39 degrees, 37 and a half. Let's see, 39, 37 and a half, right? So, or 39, 37, 30 seconds. Remember, 30 seconds is half a minute, right? So this is also 7.5 degrees on east and the west. Now, other things to pay attention to is I'm going to be asking you to look at these red boxes, and you can see kind of they're in dashed lines here, and that's part of this United States Public Land Survey. And you'll see the Public Land Survey is their areas are divided into these townships and ranges, and eventually the ranges and township and ranges are separated into 36 boxes or 36 square miles. Each one of these is a square mile, which is 640 acres, you'll see in a moment. But the red numbers in the middle designate that section. So there's section 16, 17, 18, there's 7, 8, 9, and one interesting thing is the way to find these townships and ranges, you look for the red numbers on the edges of the map. For example, anything over here towards the east of this darker red line is range 13 east. Anything to the west of this red line is range 12 west. So that would be the ranges. And so if we look for the townships, you'll see that here's a good example. So here's another dark red line. So anything to the north of this dark red line would be in township 20 north, and anything to the south is township 19 north. So that's how you'd find these townships and ranges. And I'll explain this more in a moment, but I just wanted to point these out on a topographic map. Other elements of a topographic map, so if you look down in here, you'll see that there's always an inset map of the state in which this map is found in. And then the little dot tells you what part of the state this topographic map is located, right? So that's a little locator. And then you'll also see another important thing, they'll give you scale. And we're going to talk about really 3 types of scale. One is this scale here where it's a ratio scale or a representative fraction, sometimes called a fractional scale. It says that 1 unit measured on this map is equivalent to 24,000 of the same units measured out on the ground on Earth. For example, if I measure 1 inch on this map, I'm really measuring 24,000 inches in the real world out on the ground. So that's and also think about this as a shrinkage factor. I had to shrink this part of the planet 24,000 times to fit on this piece of paper, right? So that's a fractional scale. The other scale we look at is this bar scale, this graphic bar scale. And be careful with this one because note that they always have kind of 0 in a weird place. So 0 is here. So 1 mile is really from 0 to here. That's 1 mile. And then here for feet, they have 0 right here. So you want to measure from here and then go off. Because there's a question asking you to do about 7,000 feet. So make sure you measure from here to 7,000 feet. And then same thing for kilometers. 0 sort of right in the middle. One important element of topographic maps is they show elevations on a flat surface. So this is a flat map, but it shows elevations and it indicates elevations with these contour lines. And some contour lines are labeled, others are not labeled. For example, these dark, bold contour lines with labels are called the index contours. And then adjacent contours are just regular contours. And one important thing we need to figure out is if we want to figure out the interval between each contour line. So as you're moving across these, you're changing elevation. You're either going up or you're going down. For example, this index contour here is 5,800, and the next one over here is 6,000. So that's this one here. So between this index contour and this next one, I'm covering 200 feet. And then the way to calculate the interval or the elevation of each of these contours is to treat them like steps, like you're going up a staircase. So I take 1 step up there, 2, 3, 4, 5. So I have to take 5 steps to go from 5,800 to 6,000 to cover the 200 feet. So that means that I took 5 steps to cover 200 feet. So 200 divided by 5 is 40. So each contour is 40 feet higher or lower, depending which way you go, than the adjacent contour line. So remember, contour lines don't cross. They mark equal lines of elevation, right? So you can't have 2 contours joining or crossing because you couldn't have a point that's at 2 different heights at the same time. And one way to check your calculations for contour interval is usually maps give it to you. 40 feet tells you right in here.